When we think about empty space, we pretty much imagine nothing at all, a sort of void. But in physics, empty space is not really empty. It's one of the most active and interesting things in the universe. So let's start with what we mean by empty. If you take a box and remove all the air, all the dust, all the atoms, you've created a vacuum. For a long time, scientists thought that a vacuum was simply nothing. But modern physics tells us that even a perfect vacuum has structure and energy. So firstly, from the perspective of gravity, space is not just a place where things happen. According to Albert Einstein in his theory of general relativity, space and time are woven together in something called space-time. Pretty genius, right? Massive objects like stars and planets bend space-time. That bending is what we experience as gravity. So even if you remove all matter, the geometry of space-time is still there. So what does this mean? Space has shape. It can stretch, curve, and ripple. In fact, when massive objects accelerate, like two black holes colliding, they send out ripples called gravitational waves, which were directly detected by LIGO in 2015. That means empty space can still physically vibrate. Now, let's zoom in from cosmic scales to quantum ones. In quantum physics, empty space is filled with fields. A field is something that has a value at every point in space. For example, a temperature map of a room is a field. Every point has a temperature. But in modern physics, particles themselves are excitations of underlying fields. An electron is a vibration of the electron field. A photon is a vibration of the electromagnetic field. So even if you remove all the particles, the fields still remain. And here's the key idea. These fields can never be perfectly still. Because of the uncertainty principle, there's always a minimum amount of energy present, and even in the lowest possible energy state. This leftover energy is what we call the vacuum energy. That means that empty space has energy built into it, and this isn't just theoretical. One piece of evidence comes from a measurable phenomenon called the Casimir effect, where two metal plates placed together extremely close in a vacuum experience a tiny force pulling them together. That force arises because of changes in the vacuum energy between the plates. So the vacuum isn't empty. It has real and physical consequences. So let's connect this quantum part to the large scale again. When astronomers observed distant supernova in the late 1990s, they discovered that the expansion of the universe is accelerating. This was confirmed by observations from missions like the Wilkinson Microwave Anisotropy Probe. To explain this acceleration, physicists introduced the idea of dark energy, a form of energy that seemed to be built into space itself. One interpretation is that dark energy could be related to vacuum energy. So here's a big picture. On large scales, empty space does have geometry, meaning it can curve and ripple. On small scales, empty space contains quantum fields that fluctuate and carry energy. And on cosmic scales, the energy of empty space may actually be driving the expansion of the universe. So empty space isn't the absence of physics. It's one of the most fundamental ingredients of reality. Matter still exists in space, but space itself has properties, structure, and dynamics. When you remove everything that you can remove, what's left is not really nothing. It's a fabric that you can bend, a sort of fields that you can fluctuate, and energy that can shape the fate of the entire universe. That's what empty space really is. If you guys enjoyed this video, make sure to like and subscribe. Stay curious like a child, the world needs more of it. Bye!